Welcome to the Intel Network Builders Technology V Summit series. It's time now for our session on building an OpenRAN distributed unit with Intel's FlexRAN. It's part of the 5G RAN V Summit. With more operators seeking OpenRAN-based solutions and adopting the ORAN fronthaul specification, it is important for implementers of distributed units to have solutions, including Supermicro's optimized hardware and Intel's FlexRAN software. Well, to tell us more, I would like to welcome Kevin Bross, Principal Engineer at Intel, and Yaming Wang, Director of 5G and IoT Solutions at Supermicro. Hello to both of you, and thank you very much for joining us in the session today. Yaming, what does the 5G infrastructure market look like, and what's different about the market dynamics in terms of closed versus open systems?
So let's take a look at the 5G infrastructure. A typical wireless operator's network has two major components: the core network and the radio access network, or RAN. The core network is where they will route all the incoming calls, manage subscriber accounts, and connect to the public cloud. RAN is where the end device, such as a cell phone, communicated to the network. For an operator, there are far fewer core network nodes compared with RAN, since RAN will need to have equipment to cover each cell. Normally, an operator will spend over 80% of its infrastructure investment on RAN. Based on a CapEx forecast from Heavy Reading, as you can see from this slide, global operators plan to spend over $200 billion on 5G infrastructure upgrade. In fact, for 5G, operators will likely spend even more percentage of its CapEx on RAN, since 5G will utilize higher spectrum frequency, which will lead to more base stations to be deployed. Another trend for 5G is the operators has been trying to cloudify its network to enable the cloud-type applications run in its network to generate additional revenue stream. There is a challenge for the operator. However, traditionally, the suppliers are limited to very few large network equipment makers with end-to-end solutions, not interoperable with each other. In fact, there is a movement to use open hardware platform for key RAN components such as DU and CU. And let's take a look at the disruptive solutions. So companies, technology companies such as Intel and Supermicro and operators are organized to enable an open ecosystem with lots of potential players and faster innovation. ORAN started by leading global operators such as AT&T, China Mobile. Its mission is to reshape the RAN industry towards more intelligent, open, virtualized, and fully interoperable mobile network. The new ORAN standards will enable a more competitive and vibrant RAN supplier ecosystem. Future RAN will be built on foundation of virtualized network elements, white box hardware, and a standardized interface that will fully embrace the ORAN's core principle of intelligence and openness. Another organization has been started. It's called the TIP, or Telecom Infrastructure Project. It was started by Facebook, Intel, and many operators. It has an OpenRAN working group. Its mission is to support the development of disaggregated and interoperable 2G, 3G, 4G, 5G new radio access network solution based on the service provider's requirement. So both Intel and Supermicro are belonging to the ORAN and the TIP OpenRAN organizations. And in a way, we can think of ORAN will define the specs, and OpenRAN will be more focused on implementation and lab testing. At the bottom of this slide, I'm showing a picture, a snap capture of a video that was hosted by Affirm Networks and joined by Caroline Chen from Intel and Tarek, who is the CTO of Rakuten. Rakuten built the first disaggregated OpenRAN network in the industry. He has summarized really the key benefit for the operator to move to OpenRAN is to be able to have thousands of software upgrades in their network per day, just like the cloud and the commercial internet providers doing, compared to the older ways of a slower upgrade from operator point of view.
Thank you, Yaming. And Kevin, can you explain to us the various elements of a 5G network and what the difference is between CRAN and DRAN?
Sure, I'm happy to, Guy. So in a RAN network, if you look at the slide, we have the various parts that 3GPP has defined for a RAN network. Going from the left side, we have the central unit. We have the distributed unit in the middle, and we have the radio unit on the right-hand side. And as you can see from these various arrows that are shown here, there are different opportunities for what we call splits, or different options for splits in here. Most of the 5G network is standardizing around using a definition of the DU, the distributed unit, so that it has the connection to the radio unit at what we call split 7. Where you have data that has come in and is already gone through the FFT IFFT processing at the radio unit, and then it comes into the DU, and the DU does some of this mid-level processing for the higher PHY up through the RLC processing, and then there is an interface, which is the mid-haul interface, that goes between the DU and the CU if the CU is split. And so that typically is what is shown as option 2. And then the CU, the central unit, provides some of the PDCP and the higher level functions before processing data out through the backhaul link to the core network. So again, you have the radio unit on the right-hand side with the fronthaul link talking to the DU, and then the DU does that hi-fi up through the RLC processing, and then the handoff goes over to the CU, and the centralized unit does the processing at the upper end of the PHY before processing it off to the core. And on the right-hand side, you have the UEs or the cell phones that are communicating to this radio unit. So that's what makes the whole overall radio access network, or RAN, work properly. But there are multiple ways of deploying this, and if we look at the next slide, you can see that there are 2 main deployment models. One is what they call a CRAN, a centralized RAN model, where you have the CU and the DU commonly located together in some sort of a central office or data center, where you can have multiple CUs or multiple DUs hooked together with one or more CUs, and then they are connected via switches, routers, etc., out to the cell sites, and then the cell sites provide that last mile connectivity out to the UEs. By contrast, the DRAN, the distributed RAN approach, has the CU still in the centralized location, but then it distributes the DU, so the DU sits out at the cell site. And so what this allows you to do is to have processing out closer to the RU at the radio unit, and you have less data that has to go back and forth from that cell site over the carrier's network back over to the data center or central office. And so there are these 2 approaches that are commonly used, and some operators are using a mix of each of these approaches.
Now, ORAN has defined some standard approaches for synchronization in OpenRAN networks. Kevin, can you explain what these are?
So in ORAN, they've defined 4 levels of synchronization splits. So they have low-level splits. They call them LLS C1, LLS C2, C3, and C4. So the LLS C1 approach has the DU talking directly to the RU. And so the DU gets its synchronization from the mid-haul or the backhaul link, and it provides that synchronization up to the front haul. So it essentially has to act as what we call a boundary clock. It has to provide timing from the left side, as you see, through the DU over to the RU at the right-hand side, because it's the RU that really needs to have the most precise timing out there. But the DU has to provide that boundary clock sort of functionality in an LLSC1 environment. In an LLSC2 environment, you'll have systems where you will still have the timing coming in from the mid-haul or backhaul connection to the DU, and then the DU is acting as a boundary clock to provide that functionality. But there is one or more switches or routers in a front haul network before you get to the RU. So there's an indirection between the DU and the RU in there. And so that complication in there often requires that those switches need to have synchronous Ethernet in order to be able to provide the proper synchronization to those switches and routers if you have switches and routers in the middle like you'd have in a C2 environment. An LLSC3 environment is very different. In an LLSC3 environment, you still can have the timing coming in from the mid-haul or backhaul, but the front haul network, like you have in C2, now has a timing master in it. So that critical timing path no longer goes through the DU. The timing path goes into the front haul network to that master that may be coming in through some other sort of gateway or a GNSS module that's in some sort of switch or front haul router. But the key thing is that the DU is no longer in the critical path of timing to the RU. The DU needs to have a level of timing accuracy, but the really precise timing that you need at the RU does not go through the DU in an LLSC3 environment. And then the fourth environment is the LLSC4 environment. And in a C4 environment, there is timing that happens to get to the RU some other way, such as from a GNSS antenna that is located at the RU. It's not dependent upon the DU or the front haul network for any sort of timing. That's kind of an other stuff approach. But C3 was commonly used for some of the early deployments. Now we're seeing more and more of the C1 deployments happening as well.
Thanks for explaining that, Kevin. Yaming, what are the types of environment in which we're going to see ORAN DUs deployed?
So let's take a look at a typical environment considerations. As Kevin mentioned earlier, there are two major deployment scenarios for DUs. One is CRAN, or centralized RAN. So typically that will go into a controlled environment, as you can see from the right-hand side. The equipment will go into a local data center or central office setting where the temperature is regulated and the whole environment will not need to worry too much about the water damage or dust intrusion and things like that. However, if we move to DRAN, the second scenario, the disaggregated RAN, typically the DU will deploy to a cell set. That's an outdoor environment. The environment will be more complex. For legacy reasons, a lot of operators have outdoor cabinet typically sitting under the pole or on top of a roof where the equipment will go into. Not all cabinets are AC regulated, and a lot of them do not have it. That's where the servers go into there. The DUs, for example, will need to have extended temperature support. It needs to start from minus 20 degrees Celsius, for example, or go up to 50 or 55 degrees Celsius to be able to survive in certain environment, because a lot of part of the world, some part are cold, some parts are hot. Last one is for certain rural area deployment and where you don't need a lot of equipment, the DU server can go into a IP65 box. IP65 basically means the box will be waterproof and also dust worry free. And this box will directly mount it to a pole so that it can acting as a standalone DU.
And what goes into a typical cell site?
So let's take a look at a typical DU architecture example. On the left-hand side is a typical DU with 3 layers. On the bottom layer is where the hardware, Supermicro have been building different type of DU hardware to meet the form factor and also other considerations with Intel's CPU and also acceleration card, also NIC card as well. On top of the hardware layer is the NFVI layer, that where you have the operating system with hypervisor for a virtualized environment or a Kubernetes-based container environment. And on top of that is the top layer is where the vRAN application runs. The vRAN application can be running as a VNF or CNF, depends on whether it's a virtualized environment or a containerized environment. And for typically a popular split 7-2 option, the VDU software will need to cover layer 1, MAC, ROC functions, in addition, also management functions and F1 interface. On the right-hand side is how DU fits into the cell site environment with other components. As Kevin mentioned earlier, the ORAN fronthaul has several LLS configuration options. For C1, for example, the DU need to connect directly to the RU. The DU will also need to be acting as a boundary clock, or sometimes it will be the grandmaster if it has the GPS receiver function integrated as part of the DU. Also, the DU will need to connect to mid-haul to a CU, or sometimes it's a backhaul if the CU and the DU is together at the cell site, so it's connect backhaul to the core network. Another key component inside the DU, other than the CPU and the NIC function for fronthaul and the backhaul connection, is the FAC acceleration. So typically, the CPU will offload part of the FAC function into a FPGA or eASIC card. This card will perform that function to accelerate the processing of for a lot of the 4G and 5G key encoding decoding mechanisms.
And Yaming, can you share with us more detail on the ecosystem for ORAN DUs?
Yes, I'd love to. As I mentioned earlier in the last slide, there inside the DU, there are typically 3 layers. For the ecosystem, we exactly mapped into there. In the middle of this slide, as you can see, is Intel and the Supermicro working together to have all the key components necessary for DU from the hardware point of view, including also the key CPU, FAC acceleration, and time sync card. On top of that layer is the NFVI layer, or operating system layer. We have been working with companies like Red Hat, VMware, or Cisco for this layer. Then on top of that is the layer 3, the vRAN layer, where lots of the software innovations happen. Today, there are 3 leading companies that were working closely together to realize the OpenRAN. The 3 companies are Parallel Wireless, LTL Star, and Mavenir. They're all US-based companies with years of investment in making RAN software working on an open environment. It is also noticed many of their layer 1 software is based on Intel's FlexRAN software. I would let Kevin share more about the FlexRAN software.
Thank you, Yaming. And Kevin, many of the early 5G network deployments are based on Intel's FlexRAN software. Can you explain how FlexRAN handles the L1 processing for 5G NR?
Sure. So with FlexRAN, it is a software library that Intel provides. It's a reference stack for doing the L1 processing in Intel architecture processors. And so what this does, what I'm showing on the right-hand side is an example of the chain for downlink processing and then uplink processing below that. So we bring the data in from the CU, and we do some processing in the IA CPU, and then we do some offloading to some hardware for the FEC processing, and then we bring it back into the IA processor, handle scrambling, modulation, some of the pre-coding, and mapping, remapping, etc. And then we can pass that off to the RU on the right-hand side, as you can see in yellow here. And so we can do all those things that are in blue in the Intel server processor, and then we offload the little bit that is in the tan or brown color. If we look at the uplink side, it's essentially the reverse. We get the data in from the RU, we do a bunch of processing on the Intel CPU in software, we do some offloading for the FEC decoding, and then we do a little more processing in the IA side, and we pass it up to the CPU. So this whole FlexRAN reference stack that Intel provides is what we provide to the ecosystem so that they can then go and build their hardened systems with the ecosystem players like Yaming mentioned. So they can build hardened systems that will go onto commercial deployments that are being used today around the world.
Well, Kevin and Yaming, thank you both very much for the presentation and for taking part in our session today. And don't forget to watch our other sessions in the 5G RAN V Summit. We have a session on how O-RAN innovation continues to lead the way for network transformation at the edge, and also one on enabling OpenRAN deployments with FlexRAN. For now though, thank you very much for watching and goodbye.